Okay, so we're taking a field trip to Paris. Parents, all go. You just have to fund it. We'll take them. And we're gonna go to the Eiffel Tower, and we're gonna ride the elevator. So, when we're going up, we start at the bottom of the Eiffel Tower, and we're going up. There's gonna be a bunch of us in here. And we want to draw free body diagrams of the people in the elevator. So, there's three things that have to happen on the way up. We got to go from not moving to moving. If we want to start moving up, we have to accelerate upwards. And so the free body diagram of us in the elevator, we're going to have some FG on us, and then we're going to have this big FN. I'm drawing it exaggerated. It's actually just a little bigger than gravity in an elevator because we don't want to squish people. But it would be a bigger normal force, so we're going to accelerate up. And that happens right at the beginning. We accelerate up. So 1 happens here. And then 2 happens most of the way. So the second thing we're going to do is we're just moving up at constant velocity. Bless you. If we're moving up, do we have a net force up?
Yes.
Do we have to? Can we move up with no net force? Yes. No problem. We're moving at constant velocity, right? What's our acceleration? 0. So if your acceleration equals 0, then your F net has to equal 0. Remember, force does not cause motion. Force causes change in motion. Force does not cause velocity, it causes acceleration. So these two are the same. Does that mean that you feel the same whether you're moving or you're not moving? Yeah, that's right. Hannah and Sam are nodding their heads, and that's correct. If you're moving at a constant velocity, it feels the same. That's why you're in your mom's car and you're driving at 90 down the highway. You don't feel anything. It just feels normal, right? Because you're not accelerating. You only feel acceleration. Okay, and then the last thing we have to do is, so we accelerate, and then we move constant velocity, and then up at the top, the third thing has to happen. We have to slow down and stop. So here we're moving up, but getting slower, which is actually accelerating down. It's weird because you're moving up, but you're accelerating down. So what's that going to look like in my free body diagram? Does my gravity grow? Does my gravity get bigger? No, that's the same. Can't do anything with the gravity. It's always got to be the same. So what's going to happen to the normal force on us? Sam's going like this. Yeah, it's going to be small. So the elevator stops lifting as much, and gravity slows us down. So this is a net force down, acceleration down. Okay. So that's moving up. 3 things happen. We accelerate up, then we move up at a constant velocity, and then we slow down, which is accelerating down, to come to a stop at the top. Okay, and then we get out at the top and we look around, oh, Paris, oh, yay. And then we're gonna get back in the elevator and go down. Turn to the person beside you and talk about the 3 things that happen as we go from the top of the Eiffel Tower down to the bottom. I think Addie had it there. Addie, tell us the whole thing.
It accelerates downwards.
Good.
And then it stays at a constant velocity in the middle, and then as you go, like get closer to the end, then the acceleration is up, but you just
Awesome, perfect. Let's give her a golf clap. Good job. Oh, come on, let's give a golf clap. That'd be nice, thank you. Yeah, she's absolutely right. So you accelerate down in the beginning because you get into the elevator, stay still. So in order to start moving downwards, we have to accelerate down. Then we're going to move at a constant velocity for a bit on the way down. And then in order to stop at the bottom, we have to actually accelerate upwards. And slow down. We'll say slow down to stop. Okay, so try to sketch those 3 free body diagrams. Talk amongst yourselves and see. So is gravity changing at all here? Gravity's going to be the same in all 3 situations. That's not changing. So our normal force is what's going to change. If we're going constant velocity, what would you say about the 2 forces? They're going to be the same. They've got to be equal. Benji, what's happening here?
The gravity's bigger.
Good. Yeah, this one has to be bigger, so we gotta shrink our normal force. And Leo. Leo. Hi. What happens here, Leo?
It's falling.
It's slowing down at the bottom. So how is the elevator gonna slow us down?
With tension.
Okay, there's a tension force acting on the elevator, and you on the inside, there's going to be a normal force acting on you, right? So is it going to be bigger, the same, or smaller than gravity?
Safer.
Yeah, that's right. Good. Because we're getting slower, so we're actually accelerating up, right? This is happening right down at the bottom here. So this is like 1 and then 2 on the way down and then 3 at the bottom. Good. How many people did that? You got that. Good. Okay. Look at all 6 of these now. Edward.
Yeah.
Are all 6 of these different? No. Some of them are the same, right?
Yeah.
Which 2 are the same? These 2 constant velocity ones are identical, right? Whether you're moving up or moving down, the forces are the same. Addie's absolutely right. Sam? This one is the same as this one? Yeah, you're right. If you're accelerating up, it's actually the same forces as if you're moving up getting faster or moving downwards getting slower. The forces are the same. It's accelerating upwards. And then of course the accelerating downward is the same too, right? Accelerating downward can be moving down getting faster, or it can be moving up getting slower. It's the same thing. So you really only have 3 situations here. It just depends on your direction of motion, how you draw the diagrams. One weird thing. Right now you have these 2 forces acting on you, right? Yeah, Addie. Oh, shit, I missed the best part. Yeah, here we go. Do you have gravity acting on you right now? Yes. Is there a normal force acting on you right now? Yes. Turn to the person beside you and decide, which of those forces do you feel?
I mean, you know what forces? Is the chair pushing you or are you pushing the chair?
Right.
That's like the same thing, right?
Is it?
It feels.
Riley says, is the chair pushing up on me or am I pushing down on the chair? That's kind of the same thing. But it's not, actually. I'll tell you a secret. Oh, I'll put on my hat.
Okay.
This is, okay. I'm going to tell you something. This is not Physics 11, okay? So if you're struggling with Physics 11, you might want to just fast forward this part, okay? Okay, I'm going to tell you something. Do you want to know? Gravity is not a force. Okay? Gravity is actually not a force. And what's more, you have never felt gravity. You don't feel gravity. Nope. When you're falling, you feel nothing. You can't feel falling. If I put you in a box and I dropped the box and you were like floating around in the box as the box fell, and I put you also in another box and you were out in space just orbiting the Earth and you were not falling, you would feel the same. There would be no way to tell the difference. Think about this. If I pick up this calculator and I pick up this teeny little crumb of aluminum foil and I drop them both, what will they accelerate at? At 9.8, if it's in a vacuum. If I pick up a jumbo jet and I drop that, it'll fall at 9.8. An elephant, a mouse, they all fall at 9.8. This really bothered me when I was a kid. When I learned that, I was like, that can't be right. That does not make sense. Because if gravity is a force, it should accelerate things at a different rate.
Right, because force is affected by mass, right?
Yeah, if you shove this book, or you shove me, or you shove Benji, you're gonna feel a difference, right? If you shove the book, it's gonna fly. If you shove me, I'll fly a lot. If you shove Benji, don't shove Benji. That's not a good idea. If you shove a rhinoceros, it's not gonna move much, right? So if gravity is a force, it should accelerate things at a different rate, but it doesn't. Everything follows the same acceleration.
What's going on?
That's because gravity's not a force. And actually, when you fall, you're not accelerating at all. Einstein would, now Newton would disagree with me, okay? Isaac Newton would say gravity's a force, you fall at the acceleration of gravity. But Albert Einstein, that guy, would tell you that when you're falling, you're actually not accelerating. But right now, when you're sitting in your chair, you are accelerating. You're accelerating upwards through space-time. And what gravity is actually is a distortion in space-time. The Earth pulls actually not on you, but on space and time itself. And so space and time travel differently up here than they do down here.
Weight relative to what? Earth? Up here, down here,
That's a great question. Relative to any piece of matter. That's not Physics 11. Okay, so gravity is a force, and it pulls us down, and we accelerate. And the floor pushes up on us. What do you feel? You might say, I feel gravity. No, you do not. I'll show you. I'll prove it to you. I have here a scale. Okay? Okay, now before I stand on this scale, no, I've been exercising, okay? I'm trying. But it doesn't always work that well. Okay, I'm gonna get on here. This scale is way off.
Yeah.
It's way high. Okay? Now, that's my weight, right? But what is the scale measuring really?
The weight of your
Gravity.
or your weight of your gravity.
Is it measuring the force of gravity on me?
Yeah.
Yeah. No mass.
Nope.
Mass and gravity.
That's what they tell people. We tell you that a scale measures your weight. It does not. A scale measures normal force, not gravity. I'll prove it to you. I'm going to jump up and down on the scale.
Careful.
What do you think is going to happen? No. I'm not going to break the scale. Oh,
That's a while.
I promise. I've been working out. My diet's all good. So I'm just doing. So I'm just going to bounce a little bit. Watch the needle. What happens to the needle?
Jumps.
Look, gravity is changing. It's going crazy. Right? Gravity is changing. Everybody's going to fly off the earth. No, gravity's not changing. What is changing?
Normal force.
My normal force. The scale
Right.
The scale does not tell you the force of gravity acting on you. A scale tells you the normal force pushing up on you. That is also what you feel. Right now, you're not feeling gravity pulling you down. You're feeling the chair pushing you up. Normal force. Yeah. And that's what a scale feels. So, if you're in an elevator and you're standing on a scale, will the scale remain the same as you move up and move down?
Once you're in constant force, yes. But
Ah.
in the acceleration, deceleration will vary.
Let's give Riley a golf clap for that. If everything is the same, if the forces acting on you are equal, if gravity down and normal force are the same, the scale will tell you your weight, because the normal force is the same as gravity force, and gravity force is your weight. So a scale will tell you your weight, but only if you're not accelerating. So if you're on an elevator and you're moving up, while you're moving up, the scale will tell you a bigger weight. And then when it's constant, it'll go back to normal. And then at the top, what happens when you slow down? Yeah, this needle's going to go down because your normal force has to be less. I have a worksheet for you on elevators. And that's all for the video.